if you want to sit.
Yeah, what is the microphone arrangement? Just holding the handheld microphone.
Yes, unfortunately.
You need one. I prefer it if it's one.
Okay. ¿Y tenemos una botella de agua? Sorry, we didn't pay attention to that, so. Para que la tenga, porque sí. Muy buenas tardes a todos, sean bienvenidos a esta conferencia magistral que le llamamos la Conferencia Nobel. Quisiera básicamente agradecer a las autoridades, a la universidad, a todo el comité local del Estado de México por todo el apoyo que tuvimos o que hemos tenido durante esta conferencia, que nos ha permitido tener a personajes tan distinguidos como el que tenemos el día de hoy. En esta ocasión tenemos al profesor Duncan Haldane, es el Premio Nobel de Física 2016 en aislantes topológicos. Sean todos bienvenidos y nuevamente muchas gracias a todo el comité académico del Estado de México que nos apoyó en todo esto. Yo le paso el micrófono al Sherman y los dejo con él. Gracias.
Muchas gracias, Horacio. Muchas gracias a todos por estar presentes aquí. Primero voy a decir unas palabras para poner en relieve la obra que ha hecho el profesor Duncan Haldane. On behalf of the Sociedad Mexicana de Física, it's a true honor to introduce Professor Duncan Haldane, a brilliant mind whose work has transformed our understanding of the quantum world and the very fabric of matter itself. As Professor Haldane is able to understand almost everything in Spanish because he used to watch Mexican television while he was working in California, I will continue in Spanish because he's going to be able to understand. El profesor Haldane es uno de los pioneros de una de las ideas más bellas, fructíferas y sorprendentes de la física moderna, que la topología, una rama abstracta de las matemáticas, puede describir y predecir propiedades fundamentales de los materiales que nos rodean. Sus contribuciones revelaron un nuevo orden de la materia, invisible a simple vista, pero profundamente conectado con la simetría y geometría del universo. Su obra ha transformado nuestra comprensión del mundo cuántico. Esto ha inspirado numerosos desarrollos aplicados en nanotecnología, materiales avanzados y tecnologías cuánticas. Fue formado en Cambridge y ha desarrollado su carrera en instituciones de gran prestigio, entre ellas la Universidad de Princeton, donde actualmente ocupa la cátedra de Sherman Fairchild de Física. El profesor Haldane es Premio Nobel de Física 2016, distinción que recibió junto con David Lawless y Michael Kosterlitz. Desde luego ha recibido numerosos premios y distinciones. Voy a mencionar algunos que considero que son muy importantes, entre ellos el premio Paul Dirac, otorgado por el Centro Internacional de Física Teórica en Trieste, y también la medalla Oliver Buckley, que es la máxima presea que otorga la Sociedad Norteamericana de Física en estado sólido, y es, bueno, desde luego tiene muchísimos doctorados honoris causa. Y quisiera decir que, bueno, hoy en el Congreso de la Sociedad Mexicana de Física celebramos no solo un científico excepcional, sino también un espíritu creativo y generoso que ha inspirado a numerosas generaciones de alumnos e investigadores. Y aquí quisiera platicarles un poco que hace un año el profesor Duncan Haldane vino a una escuela de de Física Cuántica que organizó el grupo de Pavel Castro en la Universidad Autónoma de Chiapas. Vino también, fue la conmemoración del 50 aniversario de la fundación de la universidad, y la visita de él nos dejó muy marcados a todos los que estuvimos, porque él dedicó toda una tarde entera a ver los pósters de todos los estudiantes y habló con todos los estudiantes, estuvo en todas las conferencias de todos los investigadores y alumnos mexicanos, nos dio sugerencias, consejos, fue a comer con nosotros, por cierto, come de chile el más picoso, el que le quieran poner, se lo come, y fue muy interesante porque también nos platicó que él pues da clases a físicos ingenieros en el primer semestre de la carrera en Princeton, que él prepara sus tareas, sus exámenes, que muchas veces tiene que calificar 200 exámenes, estaba muy preocupado porque tenía que calificar los exámenes regresando. Y bueno, pues como pueden, eso lo comento porque si él está aquí es porque de alguna manera sabe que es una figura inspiracional para nosotros. Estoy seguro que dentro de una hora su vida va a cambiar, porque pues es un ser humano excepcional, ¿no? Podría decirles muchas cosas, no quiero extenderme, pero me estaba contando ahorita que, por ejemplo, el Premio Nobel lo donó a una caridad. Entonces, es una persona de ese calibre, ¿no? Entonces, profesor Haldane, gracias por estar aquí, gracias por mostrarnos con su ejemplo de cómo en los rincones más abstractos de la ciencia más pura se pueden encontrar secretos del universo y que con ellas se pueden hacer innumerables aplicaciones en beneficio de la humanidad. Y como decimos aquí, bienvenido a su casa, a México.
Gracias. Perdón para hablar inglés. So I'm going to talk today a little bit about topological matter, but which is my own work, and the second, quantum revolution, which is this new emphasis of entanglement as a key property of quantum mechanics that seems to be giving rise to new future technologies, both in sensing and in, hopefully, quantum information processing. And then I'll move on. So let's have a look. Oops. So the key message is that as we understand quantum mechanics better, there are kind of new and strange and unexpected possibilities for the materials of the future and the technologies which they will allow are emerging. And this new understanding has been emerging in a series of unexpected surprise discoveries that have led to new ways to think about quantum materials. The way I think about quantum materials or quantum condensed matter today is very different from what we learnt when I was a student. So the modern laws of quantum mechanics were established 100 years ago. In this very short period, 1925 to 1932, and starting with Heisenberg, Schrödinger, Pauli, and Dirac, de Broglie. And the laws of quantum mechanics have so far stood the test of time. There have been no fundamental changes to the laws of quantum mechanics as we understand them since 1932. And all the tests of quantum mechanics to date have confirmed that these laws are correct. We don't know what will happen in the future, but so far no one has made their career by betting against quantum mechanics. Every time it's been tested, it's worked out. But just because we know the laws doesn't mean that we know all they allow to happen. There's an example of electromagnetism, which was finished 1864, that's 150 years ago, or 160 years ago, I guess. And, now the 20th century was perhaps the time of development of all the applications of electromagnetism. But there's a story that in the early days that the British finance minister Gladstone, who later became prime minister, visited the lab of Michael Faraday, one of the founders of electromagnetism. And someone there claims in his memoirs that Gladstone said, "Professor Faraday, this is all extremely interesting, but what's it good for?" And Faraday was supposed to have replied, "Sir, I cannot say, but one day you will tax it." And of course, electromagnetism became the foundation of technology for the 20th century. And it's still a vibrant subject. In recent years, photonic crystals, lots of lasers, of course, but that's quantum mechanics. But photonic crystals, for example, is a very vibrant new thing that started up in the 1990s. And so we keep on learning about electromagnetism. So what are we going to learn about quantum mechanics in the future? Okay, so until recently, the result from quantum mechanics that had the biggest perception in the public mind was probably the Heisenberg uncertainty principle, that you can't, if you try to measure something, you influence it. Or another idea is that, interesting idea from quantum mechanics says you can leave a room by 2 doors at the same time. From this fake quote from Yogi Berra, the baseball bard, who said, "When you come to a fork in the road, take it." But recently, this notion of entanglement has started to become recognized as perhaps the most fundamental property of quantum mechanics, perhaps even more fundamental than the Heisenberg uncertainty principle. So starting around 1980, kind of new insights into quantum mechanics started to emerge, and in condensed matter theory and experiment, new unexpected topological states of condensed matter started to be discovered. Properties of quantum mechanics that we hadn't imagined. And somewhat earlier, but quantum information theory took hold when Richard Feynman started thinking about what would happen when you made computers come down to atomic scale. And he started thinking about what a quantum computer would be. He thought it would be something that you could use to calculate quantum mechanical properties with. So these two themes of topology and quantum information theory have kind of merged. And so there's been a fusion of the fields with this new ideas for information theory coming and helping to give new ways of looking at the kind of quantum mechanics of condensed matter that we looked at. So really what the current aim is to find out how to delicately control quantum states of matter to process, for example, information, while earlier experiments to something like taking a hammer and smashing something and looking at the pieces that came out. Now you don't want to destroy your quantum state, you want to gently poke it and nudge it and make partial measurements or whatever to kind of steer it into something interesting. And so this is what people have talked about now as the second quantum revolution. And hopefully it's going to come to pass in the next 10 to 20 years. I think it's actually starting to come to pass much sooner. There's a lot of new developments in quantum sensing technology, for example, which are going to have a big impact in the next couple of years. So, what is quantum mechanics? Well, this year we recognize 100 years of what we call modern quantum mechanics, which is rather different from the first version of quantum mechanics that was a guess by Niels Bohr. So we still see this idea of Niels Bohr thought you could view the atom as quantized orbits, like little planets going around the sun, electrons going around the nucleus, but now their angular momentum was quantized, and so they could only travel in certain fixed orbits around the nucleus. And these were called like orbitals. So the idea of the orbital has been inherited. I'm going to talk about orbitals, but it really comes from a complete revision of the Bohr formulas, which were kind of empirical, starting with the Heisenberg and then the Schrödinger picture in 1926. So Bohr's little orbitals, around the nucleus, now become essentially a box which can contain an electron if it's occupied and not if it's empty. And when we have such a system, we don't know exactly where the electron is, but we just know it's in the box or it's not in the box. So the Heisenberg uncertainty principle turned Bohr's orbit into a fuzzy cloud centered on the nucleus. But going back to the earlier language of the orbits, we call the box that's the orbital. Okay. So the electron, an orbital is a kind of box that can contain an electron. And so it's either empty or filled, which is of course, I've missed out the fact that it's going to take 2 electrons to fill the box completely. But if we just think of a box which is empty or filled, that's the qubit, which is either a 2-state system, in this case empty or filled. And in this picture, okay, so there we have the hydrogen atom, hydrogen ion, with the box empty, and then there's an electron in it to make the hydrogen atom with the box filled. And we can now image these orbitals. This is not the lowest orbital of hydrogen. This is a Rydberg orbital, a highly excited orbital of hydrogen, which are being used for qubits very usefully these days. But anyway, so we can image this fuzzy box, and there is an actual image. Okay. So the Pauli exclusion principle says that 2 electrons can't be in the same state, or roughly speaking, they can't be in the same place. And many people ask, where is quantum mechanics in our everyday life? But in fact, the fact that I'm not falling through the stage towards the center of the Earth is purely to do with Professor Pauli's exclusion principle. And it's basically, if it wasn't, the atom is 99.9% empty space, and it's not electromagnetic forces that are kind of keeping me from falling through the floor. It's the fact that the electrons which are bound to the atoms in the sole of my shoe can't, according to Pauli's principle, can't occupy the same space as the electrons bound to the floor of the stage. So this is, of course, what Newton would have just said. This is the normal force. Gravity is pulling me down, and the stage is exerting an upward force on my shoes to balance it. And so that was sort of obvious to Newton, but he had no idea where the normal force came from. It was just a kind of normal, obvious, everyday observation. But of course, the normal force of Newton is precisely just the quantum mechanical result of the Pauli exclusion principle that prevents gravity pulling us down to the center of the Earth, because our electrons can't occupy the same place as the electrons in the floor. Okay, so the Pauli exclusion principle says that 2 electrons or fermions can't be in the same state. So what defines that state? So in addition to the position, the state of an electron depends on the direction of something called its spin. It's something like a spinning top. And so it's got the spin of the electron is pointing in some direction. And we can put 2 electrons in the same box or the same orbital if their spins are pointing in exactly opposite directions. So because having spins pointing in opposite direction means they're in a different state. So we can't tell what direction they individually point in, just that they have to be in opposite directions. And if we swap the 2 electrons around, there's a complex number, the wave function, that characterizes the quantum state changes to minus itself when I exchange two electrons, and this is the fermion state, the property of fermions that can't occupy the same state. So the maximally entangled state of the two electrons is precisely this up-down minus down-up combination of states, and it could equally be side left-right minus right-left, and this is an interesting feature that we don't know we only know which direction a spin is in if we measure the other spin. We'll always find that the second spin we measure is pointing in the opposite direction. So high school chemistry says that each atom has got lots of boxes or orbitals into which the electrons are placed, and there's an analogy to buildings and apartments and rooms, etc. And Pauli principle, of course, allows two in each box. But this is kind of just a simple, in fact, this is almost all the quantum mechanics until recently that a chemist would have had to know, because we're just kind of filling these orbitals up. And so it's a very key thing, okay. So the chemical bond that binds atoms into interesting clusters like us is a maximally entangled state where you have the two electrons are basically pulling the two atoms together in the hydrogen molecule, and they're sitting in between. It's their electric force is kind of pulling the two nuclei together, and one is up and the other is down, but or more correctly, then this mixture of up, down, minus down, up, the maximally entangled state. So the chemical bond is the example of the maximally entangled state. So entanglement seems to be the central property of quantum mechanics in this new interpretations. And it's now recognized as the central property first pointed out by Einstein. Einstein's got a contribution for quantum mechanics for explaining the photoelectric effect in 1905. And that's what his Nobel Prize was for, but he made this very important contribution to quantum mechanics by pointing out that it predicted entanglement. So now it's viewed, entanglement was for a long time a philosophical issue to be debated by philosophers of science, but now it's actually viewed as a fuel which will drive future quantum information processes and such technologies. So entanglement has come a long way. And of course, Einstein pointed out entanglement not because he wanted to say what a fantastic properties quantum mechanics has. He wanted to say this property predicted by quantum mechanics is so crazy it can't possibly be true, because he didn't feel that quantum mechanics, it violated what we now call local realism, which he felt it couldn't possibly be a proper fundamental theory of nature. And he thought and he pointed out it can't be right because it predicts entanglement. He called it spooky action at a distance. It's an interesting word. Every language seems to have adopted a separate word origin for entanglement. Verschrankung in German, intrication in French, and entrelazamiento cuántico in Spanish. Okay, I didn't translate spooky action at a distance into Spanish. But yeah, so in fact, around about 1935, there was one day when I guess no country had been invaded or something, the news was a bit low, but Einstein's collaborator Podolsky went to the New York Times and told them that Einstein had shown quantum mechanics was wrong, and this made the headlines of the New York Times that day. They proposed this, what's now called the Einstein-Podolsky-Rosen experiment, which basically takes the entanglement of the chemical bond and imagines what would happen if I could stretch this chemical bond very, very widely apart without disturbing the entanglement. Now, when the chemical bond is very short, there's quantum energy gaps that protect it, and it's very stable. But if you now stretch this thing and attempt to keep the particles entangled, it's very fragile, large distances. But Einstein worried about the apparent violation of relativity. If this pair, which is, according to quantum mechanics, is equally up, down, and down, up, is stretched, and you do a measurement on one side of it, it'll immediately imply that a measurement on at the other end of the entangled bond would give you a spin pointing in exactly the opposite direction. And he felt that was like somehow a violation of relativity, that information or something was transmitted instantaneously. Actually, it doesn't violate relativity because you can't use the EPR experiment to transmit information. And the relativity principle says that no information can be propagated at faster than the speed of light. I can take a laser beam, I can take a high-powered and very sharply focused laser and point it at the moon and make a spot on the surface of the moon. And as I move my hand with the laser, I can scan the laser point on the moon, which can move across the surface of the moon faster than the speed of light. But it doesn't mean that someone on the moon could use that to communicate something at faster than the speed of light to somebody else. Right? No information is being sent faster than the speed of light. Actually, so Einstein was very angry with Podolsky. He never talked to him again. He felt that he'd committed an unpardonable sin he felt that physicists' dirty laundry should not be exposed to the public, he called it. So it was done without his permission, and he was very upset. He continued to work with Rosen afterwards, but not with Podolsky. Anyway, so Einstein, Podolsky, and Rosen thought you could make an EPR pair of particles basically by starting with a pair of particles which were bound together in a little box, shall we say, like a nucleus or whatever. And then suppose we switch the box walls off, and the particles are now free to move apart. And by conservation of momentum, they must move apart in opposite directions. And they will keep on going. But the idea was that they were entangled before, and the EPR experiment says we maintain the entanglement, and they go on and on for large distances. And so, as I say, Einstein felt the decision about whether the spins were up, down, or left, right, or whatever had to be made at the moment they split. And the work after that was devoted to showing that you could make decisions about which direction to measure their polarized spins in long after they split apart, and do tests of quantum mechanics that way. So we saw 2 recent Nobel Prizes a couple of years ago from some of the foundational experiments. Einstein's ideas were kind of put into more firmer form by David Bohm and then John Bell, who came up with very positive kind of tests to see you could test whether Einstein's idea was right or wrong by saying that if you assumed local realism, that you could put a bound on various measurements you could make, and he showed that if you could do certain measurements and show they were outside the bounds implied by local realism, that was a proof of quantum mechanics against Einstein's ideas. So anyway, so it worked out. But of course, the problem is that the entanglement over distances large compared to the chemical bond is extremely fragile against decoherence by coupling to degrees of freedom of the environment. So the experiments by Alan Aspey, which I guess put the final touch to the Bell ideas, was done not with particles and spin, but light, with circular polarized or linearly polarized light. And light can travel for huge distances without interacting with the environment, as we see that light coming from the shortly after the Big Bang, when the universe went transparent by the atoms forming, is still coming towards us. So light can travel long distances, and the EPR experiment has been shown to work even between things in orbit and the Earth. Okay. So there's of course a large amount of work on trying to use this for transmitting quantum cryptography codes and things in a secure way. Okay, so what is quantum information? So classical information is stored in a bit, which is a switch which is either on or off, 0 or 1. And you can view that as a large number of quantum spins, which are all wanting to point the same way, and all pointing up is 1 and all pointing down is 0. But the quantum system, a single spin or a single two-level system, can be viewed as a spin that can point in any direction on the so-called Bloch sphere. So there's a lot more information content rather than just on, up, or down. In the sense you've got this whole direction you can point in, but it's a fuzzy direction. You can't. If you measure, if it's in one direction, you can choose to which direction to measure the spin along. Anyway, so one of the big things in the quantum information is that it differs from classically stored information. Is that classical information you can copy it many times, right? So if people are copying their song from the internet, they'll say, well, they didn't lose anything, I just made this copy, and you can make as many copies as you want. And classical information is actually kind of difficult to get rid of. If you want to erase it, like you want to get rid of your computer and get your bank details off it, you have to do quite a lot of work to clean out your hard disk drive, to recycle your phone. But the qubit information is much richer but much more fragile, and it has two important things. It can't be copied. If you store information in this qubit, which is viewed as a spin pointing in some direction, and that encodes some information in the direction, you can't make an identical copy of your qubit. It's called the no-cloning theorem. But interestingly, you can transport the information by so-called teleportation, which people like, where you can take a qubit over here in a given state. You can take a highly maximally entangled pair, now called a Bell pair, and you can use it so that you can transmit the information. You can reconstruct whatever the state of your initial qubit over here is onto another qubit over there at the expense of destroying the information locally. Okay. So let's see. So there's a no cloning theorem. And teleportation is rather interesting. This is why people start to think about entanglement as a resource for quantum computation or information processing. We have a local qubit, which we're not allowed to measure it, because if we measure it, we destroy the information. we want to copy it. Our copying mechanism involves forming this entangled pair, a long-distance entangled pair. So entanglement is only becomes something useful when it remains entangled over large distances, as compared to molecular distances. Right? But out of this, you could make an experiment, a measurement of both of the joint state of one end of your entangled pair and your target qubit, and such that there are 4 possible outcomes to that experiment. And to transmit the thing, you pick up your telephone, classical communication, and call to someone at the other end of the entangled pair, and tell them what exactly your measurement was, what the result of which of the 4 possible results of the measurement you got. And based on that, they can work out an operation on the other end of the entangled pair, which will provide an identical copy of the one which was destroyed in the experiment done at the left side. So this is this amazing idea of entanglement, which is a kind of strange idea. Okay. So the remote qubit that's left over on the right-hand side is a perfect copy of the original, but now the 2 qubits which are on the left-hand side kind of contain no useful information at all. So, or they're entangled, but they're short distance entangled. So you paid the cost of the long distance. You had to provide some resources to create the long distance entanglement, and you have used that up in doing the teleportation. Okay, so that's why this idea of entanglement is one thing. Okay, so that's the idea of entanglement as the fuel for quantum information processing. Okay, let's move on. Okay, so it's actually quite complicated to make an entangled pair. I can start with 2 unentangled qubits, both in the same state. To make them entangled, I have to bring them into contact using what's called a gate, a specially constructed gate, which switches on a local interaction between the 2, and I have to switch it off at a precise time later. And if I get the time exactly right, I'll have created this up-down minus down-up entangled pair that I can then use them for Bell processes. But it's a rather delicate procedure, and in principle, the topological route to quantum computation would make it be a much more robust way of doing this. Okay, so back in 1980, condensed matter physicists were playing around, and they thought they knew about everything. They'd understood magnetism and solids and crystals and phonons and photons. So people thought they had a basic understanding, and that's when, the hubris gets called short when something completely unexpected gets discovered. And actually, 2 unexpected discoveries happened around that time, which both turn out to involve topological states of quantum matter. The most important of being, of course, the quantum Hall effect by Klaus von Klitzing, and which at the time had no obvious relation of any kind to the thing I found in magnetism. Okay. But these things have turned over the last decade or 2 have blossomed, and huge amounts of different kinds of topological, these states of matter have started to emerge. One can say that in some sense the topological states are states of matter where quantum entanglement is playing an important role. Okay, so what's topological matter? It differs from ordinary matter because it has entanglement properties, or properties that can be classified by whole numbers. So if you have matter that can be described by these numbers, then ordinary matter might be 0 or 1, but suppose you've got some kind of matter that is classified as -2, and regular matter has a boundary between it and regular matter, which is classified by 0. You can't get rid of that boundary. You can't go continuously from 0 to -2. And so that's the essence of topology. Topology mathematically is classifying different things by simple whole numbers. And the whole numbers can't vary at all, so that gives you a kind of distinction between different things. So topological properties of materials can't change continuously, which makes their properties robust to small amounts of disorder or dirt. So that's quite a difference from the usual kind of materials we work with, like silicon wafers, where the people in this picture are wearing all these spacesuits and things. Those are not so much to protect them from the noxious chemicals in the production, it's to protect the silicon chip from little bits of hair or spit or something coming off the people, because one little piece of dirt on the silicon chip can ruin it. So that's why this stuff is very delicate. So mathematically, the classification of closed surfaces by the number of holes in the surface, called the genus, is the original part of topology. And in a sense, there's holes come in, at least not on an atomic scale, but on a kind of larger scale thing. Holes in surfaces come, you've either got a hole or you don't have a hole. They're not 0.5 of a hole. So this is the famous theorem of Gauss. So Gauss discovered this important theorem that if you take the surface area, if you take a sphere which has a surface area 4 pi r squared and multiply it by something called the Gaussian curvature, which is 1 over r squared, you get 4 pi. Now that seems to be a trivially true statement, but what Gauss discovered, it was true not just for a nice round sphere with a uniform Gaussian curvature, but if I change the shape of this sphere and turn it into a banana or something, the Gaussian curvature map will be much more complicated, but you'll still, when you integrate the Gaussian curvature over the surface area, you'll get exactly 4 pi, if there are no holes. And then he discovered that if there was a hole in it, like a bagel, if you look at a bagel, it's got regions of positive Gaussian curvature on the outside, and the inside of the hole has negative Gaussian curvature, and the two parts just balance to give you exactly 0. And then you get these other shapes here. So this was a kind of, Gauss thought this was one of the most amazing discoveries he made in his whole mathematical career, actually. Mathematicians like to take a straightforward thing and make it much more abstract and complex. And how this relates to quantum mechanics is that the mathematician Chern, he generalized the so-called Gauss-Bonnet theorem I described to a much more abstract form of curvature and to much more dimensions. And anyway, he came up with this generalization of it, and it's a generalization of this that turned out to have importance in quantum mechanics, not the actual donuts. Okay, so in recent years, we've understood that it's been realized that quantum condensed matter can exhibit unexpected properties, which are somehow associated with long-range quantum entanglement. So trivially, if I take something that's trivially entangled, it means that if I do a measurement on the left side of this green rectangle, it won't really affect a measurement. The result of the measurement on the left will not affect any measurement made on the right side. In real life, there's a slight kind of blurring at the boundary where the dotted line is, But in mathematically, a trivially entangled system can be decomposed into a simple product of the two right and left parts. And you can just separate it. But the topological states have these edge states which can't be got rid of. And so if I try to cut something topological in half, it'll resist for a while because they have to do a certain amount of damage to it to break it. But if you do manage to break it, you'll eventually find new topological edge states on each of the two new surfaces you exposed. It looks a bit like trying to separate the north and south pole of a magnet, but it's not exactly the same as that. But you can see that in a sense these edge states are due to entanglement going across the whole sample and having to be terminated at the edge. Okay. So topologically trivial states of matter can be assembled by bringing the atoms just together, stacking them together, putting them in contact, but they're not entangled, right? But topologically, non-trivial states can't be smoothly connected to free atoms which are split up. At some point, if you bring the atoms together, the electron boxes or the orbitals which were centered on the atoms have to get rearranged in interesting ways to form the chemical bonds. And if there's something topological, you can't avoid some energy gap closing. Okay. So where I came in on this is that in heavier atoms, in groups of electrons in the same set of orbitals, the same floor of the apartment building that we described for the periodic table, they like to go in spin parallel. So you start to fill one of these arrays of neighboring boxes, d orbitals or f orbitals. And initially, when you put the electrons in, they like to go in parallel to each other. So they start to add up to form a large spin, and now there's this whole issue about rare earth magnets, which is now a problem between Mr. Trump and Mr. Xi. Rare earth magnets have f orbitals, so you've got 7 electrons are lined up all pointing parallel to each other in the strongest ones. So the spins kind of behave like a spin, but they all point, lots of spins all pointing the same way, and they become more and more classical, behaving as they get longer and longer. But the total length of the spin has to be a whole number times 2s times the individual spin, which we classify as 1/2 for the electron. So this large spin is either a whole number, even or odd number of things. And in the past, people thought that since large S was classical and S equals 1/2 was quantum, they had the idea that the measure of how quantum you were was like 1 over S, 1 over the spin. So large spin, 1 over it goes to 0, so they thought of 1 over S like Planck's constant. And they didn't realize that spins actually don't vary continuously, they're integers. And this was the shock which this thing I discovered proposed. So the original idea of magnetic states is like in the upper thing. You've made something called an antiferromagnet, where this one won't pick up a paper clip, where you kind of have the spins in neighboring atoms up, down, up, down, up, down. But they're really just assembled together without any. And it turns out that the topological state for a spin 1 system, instead of the spins behaving like in the upper picture, the spin 1 really breaks apart into 2 spin halves, one of which combines with the neighbor to form a bond, And when you see that, you get left with half of a spin 1, a spin half at either end of the system. And there's essentially an entanglement. It's not just a simple assembly of atoms. And this is a later version of what I discovered put into a much cleaner form, so-called AKLT model, by my future colleagues at Princeton. But this shows you the example that there's something strange at the edge of the chain. You started off with these spin 1 objects on each atom, but you got left with half of them, a spin half object on each, at either end of this chain. So this was this was actually found by coming at this problem from a very different angle from the standard magnetism way of looking at it. And it was actually turned out to be an incredibly controversial thing at the time. A lot of people in the magnetism community kind of denounced this as complete nonsense. But I was shocked too when I discovered that the spin 1 chain had a gap, a quantum state with an energy gap, while the spin half chain was known to not have an energy gap. And like I say, it's the details are kind of not important, but science is based on controversy, and things like this had changed the way of thinking about a lot of these problems in magnetism. And so controversy in science has to be resolved by experiments, and a lot of people got involved in this controversy on either side, or just wanting to come up with a technique to come up with an answer. And for example, material scientists built nickel atom chains, which is a spin 1 chain. And finally, there was neutron scattering work that really validated my theory on this. But the key thing is controversy has been very good for science. It makes lots of people get interested in a topic, and it leads to new developments of new techniques, which have all turned out to be important afterwards. So the picture of this whole thing is that you can imagine, you might say initially that hands come in pairs, assuming that people haven't had accidents. And but then you could violate that by having a line of people all holding hands, but there's one hand free at either end of this chain of people, and they're kind of widely separated pairs of hands. Okay, so there was the kind of picture in my Nobel Prize certificate. And we'll come back to that. So you want to see it again? I would note that the watercolor is showing this later version by Affleck, Kennedy, Lieben, Tasaki of the state I found, which is a cleaner one rather than my original form. But anyway, there you go. So the quantum holes, the other thing that happened was the quantum Hall state, the discovery of the quantum Hall system, and I'll have to move on rather quickly. This has turned out to be incredibly crucial. This was recognized very quickly for Nobel Prize because it ended up revolutionizing our system of units. Before, the kilogram was basically controlled by France. Mr. Napoleon, the Emperor Napoleon, ordered one made, or they had made a copy of his, but the kilogram was a lump of platinum kept in a safe in Paris. And but now, so in principle, if your market trader was swindling you, you had to go to Paris and say, can you check my kilogram against the official kilogram? But now, using the quantum Hall effect and something else, the Josephson effect, we can now make a completely quantum device to measure the kilogram called the Kibble balance, and every country can have its own guaranteed identical kilogram now. Okay. So the topological nature of the quantum Hall effect took a long time to become clear, but it should have been clear right at the beginning. In fact, this picture I'm showing here, in more recent talks, I recognize that actually almost everything you need to know about the quantum Hall effect is contained in this picture, but in a magnetic field, which was probably in the last thing, electrons go round in little circles, and if they're confined to a two-dimensional plane. In 3 dimensions, they spiral along the magnetic field lines, but if they're bound into a two-dimensional surface, they will, with the magnetic field going through it, they will go around in little circles. And so if you put them in this little region of a 2D plane, and it's got a boundary, and quantum mechanics says that periodic motion has to be quantized, so we can approximate that by saying all the electrons have the same, going around in circles of exactly the same radius. Then if they get to within a radius, if the center gets to within a radius distance of the edge, they start to hit the edge. Inside them, in the bulk region, they will just sit where they are and go around in a little circle. But when they get to the edge, they'll bang, bang, bang around the edge in a circle, skipping orbit, and they have this very interesting feature that they'll go around, the edge states will travel around the edge in the opposite direction to the orbital motion in the bulk. And the crucial thing here is that it's one way. It's very unusual kind of edge states where things go, it's like a one-way street, right? It's because time reversal invariance is broken by the magnetic field. If the magnetic field is pointing up, they'll go around one way, and if I reverse the direction of the magnetic field, they'll be going around in the other way. And the quantization due to periodic motion gives rise to a gap, a quantum energy gap in the bulk. But the crucial thing is at the edge, the Fermi level, the boundary between empty and filled states, is pinned somewhere in the edge. And this means that if I switch on the magnetic field, I don't have to make it perfect. I don't have to get it to a perfect value to get the bulk gap. I just need to pin the Fermi level somewhere in this energy gap, and there'll be a range of magnetic fields which do that. And as I change the magnetic field, the other amazing thing is that states, orbitals, the boxes which contain the electrons, flow down the edges, flow in and out of the system as I change the magnetic field. Because if you go around the edge of the system, the electrons satisfy something called periodic boundary condition as they go around the edge, and that's affected by how much magnetic flux goes through the central part of the thing. So actually, almost everything about the quantum Hall effect is contained in that picture. But this stuff started to take off, right? There was a few years after the discovery of the integer Hall effect, there was a much more amazing thing called the fractional quantum Hall effect. And here's a device that it was discovered in, and you can see that the forgiving nature of a topological state in there, the maker of that device wouldn't be able to get a job in an Intel fab by presenting it as an example of his soldering ability. But that's okay. This stuff doesn't require perfect, clean samples to occur because of this stability of a topological state. It's protected against a certain amount of disorder. And okay, so this had all kinds of weird stuff in it. It's got elementary excitations, which are empty orbitals, but in the Laughlin state, it turns out that, maybe I've got the picture here. In the Laughlin state, there's zi minus zj to the m. When you read that carefully, a filled lambda level m is equal to 1, which indicates that each electron is occupying one state. But when m is equal to 3, it actually means that each electron is occupying 3 states. So that's why at 1/3 filling, you get this system, because you've used up, every electron has used up 3 orbitals, and by the time that once you've filled it up to 1/3 filling, there's no more room to put electrons in, because you've used up all the orbitals in groups of 3, which was amazing. And in any case, this has some of these remarkable properties, which we now call fractional statistics and fractional charge. And this stuff has been recently demonstrated. It's taken time to demonstrate some of these ideas, such as fractional statistics, but they've now become kind of clear, and these are kind of, I don't have time to go into the direct effect, but basically, when you braid these things around each other, you pick up interesting, non-trivial phase factors when you do it. So where does this come for quantum computing? The Laughlin state and other early states of the quantum Hall effect turned out to be what we call abelian quantum Hall states. But then a new class was discovered called non-abelian. And they can hide quantum information in their entanglement structure. And in principle, some of these states can support universal quantum computing, but they haven't been demonstrated experimentally yet. We believe that the so-called Moore-Reed state is one of the cases. And this led to this proposal for topological quantum computing due to Alex Kitaev, where you stir up the information that's stored in this system by having these little non-abelian quasi-particles. So what's actually going on here? It turns out the simplest example, you can have 4, this is a qubit. There's 4 objects which we now call Majorana zero modes, which can't be created locally. You can create a pair of them locally, but they're objects that when if you want to, you can create 2 of them on top of each other, and those are quite, but then if you pull them apart, you can split them into half things. So these are actually going to be half orbitals. The amazing thing is that these are going to be half of an orbital. That's kind of an incredible idea. But when you pull these things apart in a single orbital that could either contain an electron or not contain an electron, you pull it apart into 2 half orbitals, and the information about whether it contains an electron or not before it was pulled apart is hidden in this entanglement pattern. And so there's hidden information, and I could make exactly the same pattern by pulling them apart in a different way. And the hidden information is there in the history of how I made it. So let's quickly move on. Okay. Let's see further. Yeah, it's okay. There's a thing. So actually, most attempts to make qubits have been completely different from this. The only people who were pushing the topological stuff were Microsoft. Now they made a big announcement of an architecture based on this, but we don't actually know whether it works or not yet. We'll see. But at least one player in the game is trying to make topological quantum computing. The other people working on their regular qubits say, it'll never work. But anyway, so what is actually going on here? This is a very strange thing that before I said we had this idea of the orbital, a box which either could be empty or filled. And what Majorana discovered, He was a very interesting physicist who was a bit strange. Fermi wrote his paper for him because he wasn't getting around to writing it up, and then he disappeared. But basically, it allows, in the modern language, it allows for this orbital to be pulled apart into two half orbitals. Now, what could be weirder than half of a box, right? This means that if I kind of put electron into one half of it, it is also occupying the second half, right? And there's an entanglement pattern which shows how where the two half boxes were originally together. And okay, so the issue is that if you take a filled box and pull it apart into two halves, or an empty box and pull it apart into two halves, once it's separated, you can't tell the difference. You can't tell whether it was empty or filled when you do it. So the quantum information content, up or down or empty or filled, has been completely hidden from the environment. And so you can't, and the idea here is that interaction with the environment can't destroy this information because it's not visible. To make it visible, you have to bring the two parts back together. And how do you process the information? It turns out you need two pairs of these things, or four of these Majorana modes. Then the qubit state, that they could either be both empty or both filled, for example, would be a qubit. You can't mix states with even and odd numbers of electrons. So, but in any case, this is the idea behind topological quantum computing, which is very, very strange, but I think it's an amazing idea. I'm getting to the end, so I would say that physicists come up with all kinds of crazy ideas, and they love them. Technologists have the duty to they have to look at these things with a little bit of grain of salt. It's a cute idea, but is it going to be practical? And but at least on paper, the topological protected qubit is a solution to the robustness against decoherence. But of course, fusion is on paper the solution to our energy crisis too. So there's a lot of difference between something that works on paper and something that works in the lab. And but so technologists and entrepreneurs need to be, of course, skeptical about scientists' great, beautiful ideas. But at least Microsoft have not been skeptical up till now. And I personally believe it's a realistic dream, but maybe it will never happen. But anyway, so quickly, the Microsoft version involves something called a spin-orbit coupled superconducting wire, which is coupled to a superconductor and a magnetic field. And the crucial thing is that the electron orbitals can be split into these two half boxes. It can be done mathematically as a completely mathematical operation if they're close to each other. As in this picture, the orbitals have been split into a green and a purple part, which are somehow like the real and imaginary parts of a complex number. But the amazing thing that happens is that when you apply this to a superconductor and make an interaction, you can cause the orbitals to recombine. A red and a green part is a combination into a standard electron orbital. But what you see here is exactly the same picture as was shown up in the original spin chain I worked on, that by splitting the orbitals up into Majorana pairs and then regrouping them in a slightly different way, that now has left a half an orbital physically separated at a large distance from the other one, is exactly a generalization of the spin chain, except it's a much more remarkable thing to split an orbital into two half orbitals than to split a spin one into two spin halves. But So the main issue in these things is making these orbitals or Majorana zeros leak into they're not, in the toy model, they're perfectly localized at the ends of the chain. In real life, they kind of exponentially leak in, and part of the difficulties in the Microsoft setup has been to make the decay length for which these edge modes have to be sufficiently far apart from each other, much larger than the decay length for decaying into the bulk, and that's the technical issue, just like the plasma instabilities are the technical issue in tokamaks and things. So anyway, up to the end. So out of all this stuff in this quantum Hall business, there was a lot of unexpected mathematical structure that emerged. I'm a toy model builder who builds little toy models of things, which actually are simple enough to calculate with and show you the possibility of very interesting effects. And crucially, you need actually these material scientists to do this fantastic work in building the toy models, which is the new wave of material science. Anyway, so, and finally, I have a motivational message to student audiences. In this thing, my work and things I discovered were basically luck. I wasn't expecting to discover what I discovered. I can trace a progression of why I took a path that led me next door to these something unexpected. But I think that's true for all basic science research. If you give people the chance to, maybe you have a project that you have to work for a final goal, but sometimes if you give people 10 or 15% of the time they're allowed to explore stuff that emerges on the side, unusual or odd things may appear as part of your path towards your project. If you've got the time to examine and find out what exactly something a little bit strange is, most of the time it'll just be something slightly interesting and a little bit strange, but very occasionally it'll be something that no one expected to find. And that's how these amazing discoveries get made. So I view that anyone working in basic science, if they have the right preparation and the right luck so their research path takes them past something that no one was expecting to find, anyone has a tiny but non-zero chance of finding something amazing that eventually changes the way people think in their science field and gets recognized with a Nobel Prize. And of course, you need preparation, you actually need commitment. I had to fight. Initially, I was unable to publish my papers because of got 3 rejections in a row, people denouncing it as nonsense. But looking at the original paper, which then never got published, I find it's explained clear enough. But the language was a new language which was not compatible with the old language, and so you also need to fight. You need luck, preparation, and commitment, and these are exactly what you hear about in business school too. You have to make something out. But anyway, that's my view, and I think anyone working on basic science has got some possibility of stumbling across something totally amazing. Thank you.
Okay, so thank you very much, Professor Haldane, for this very beautiful talk. That I think it's the best explanation I ever heard about topological materials. Very simple. So we have time for a couple of questions. Okay, go on, please. Maybe if we have 2 microphones for the audience.
Hi, Professor. I want to start by thanking you for your time, your brilliant conference, and sharing your knowledge, I guess, with such charisma, enthusiasm, and human warmth. I am Enrique. I study physics engineering at Universidad Iberoamericana down the highway. And I guess my question is, what is your view on the relationship between elegant theoretical models and practical applications? How should one navigate the tension between exploring abstract ideas and the need for applicable results?
Well, I think the abstract ideas have to be made more concrete, and that's what the toy models, not necessarily mathematically elegant models, but models that you can understand, you can work out what they actually do. And what I learned from my mentor, Philip Anderson, was that one should remove all the unnecessary details. I mean, you look at an experiment, there's all kinds of, there's issues with the material, how it's done. It's never clear what the right question to ask is. I mean, in science, the issue is not finding the right answer, it's finding the right question. Once you found the right question, it's just a technical issue to find the right answer to that question, right? So what we don't know when we approach some problem is what questions to ask. And what I learned from him was that I should try to remove as much, identify what details are likely to be unimportant, and remove them from the model. And if the model has lost the physics you're interested in, then you know that something you removed was crucial. And if it hasn't, then you know you didn't need to worry about the details of the thing. So the crucial thing is to get some kind of understanding, and simple toy models are a way which are simple enough to solve and show up, and can possibly show up quite unexpected behavior. And so what the trend is now, it used to be that toy models were viewed as theorist games, while real people did ab initio calculations very accurately, etc. And it turned out, for example, in this topological game, all the ab initio calculation people missed the fact that they had interesting edge states because they hadn't even thought about it, right? So you need something like the simple model to show you, my gosh, this model shows interesting edge states. And why is that? And then understand it's something to do with topology. So simplification is the way to understand, to model things. And you're not necessarily after accurate modeling, you're after conceptually accurate modeling that shows you what's going on. Yeah.
Thank you very much.
We have another question there.
Micro.
Okay, wait, here, then here.
Is this turn up? All right. First of all, thank you very much for this. Oh, so sorry, I'm a little bit nervous. Thank you, but it's like motivating. Sorry. First of all, thank you for this wonderful talk. I don't know what I have to say. It's really a great privilege to listen to you here today, and that try to have the privilege of listening to these ideas. So now for my question is, with these recent advances, with this recent boom of quantum information theory and the ideas of topological superconductivity, do you think that we can bring us together the ideas from quantum information theory and topological superconductivity for finally get a complete microscopic theory of high temperature superconductivity? If so, what is the state of the art on this topic? Thank you.
Okay, I guess high temperature superconductivity has this problem that it's all being shown by these copper oxide layers. One of the difficulties in high temperature superconductivity is not having enough different materials to show it, so we can judge what aspects of the copper oxide layer are important and what are the details. That's the superconductivity. High TC is still a problem. There's still people claiming to, they're going to have a solution. I've heard recent claims that spin liquids are now going to do it. Well, things are open really, but maybe, and there's actually new kinds of ways of constructing quantum states using AI and things. So who knows what's going to happen, but it's still a murky field. There's still lots of people fighting each other, and in high temperature superconductivity, it's actually been very bad for young people's careers, while the topological physics has actually been very good for young people's careers, because there's been lots there for different people to explore and discover, and high TC became a problem of too many people fighting because there wasn't a very clear, not a totally clear model. And so being able to, if high TC has a few more sufficiently different examples, then we would be a lot better in knowing which bits of the model to keep and which bits were not. Yeah.
We have time for one question. Yeah? Microphone? Please. Or maybe you can use my mic.
Thank you so much, Dr. Haldane. Anyway, I'm not sure if I'm dreaming too high, but as you say, it's a beautiful dream. Your model showed that band topology can program robust properties even with zero net magnetic flux. With current engineering tools, how far do you think we can design bands and interaction to realize specific quantum phases? For example, fractional Chern insulators or out of equilibrium topological phases. And what are the key bottlenecks today and the most promising opportunity? Thank you.
Well, there's a huge amount of work on the twisted bilayer graphenes and moiré materials, and it's just amazing what comes out of material science. So condensed matter is a very lucky subject that there's actually experiments happening all the time. Every couple of years, some unexpected new experiment shows up, like the twisted bilayers, and we get guidance on experiments. Other areas like string theory, they don't have any guidance from the real world to know exactly what the right directions are. So condensed matter is a subject where you can have a nice combination of experiments, material science, toy models, now material science building toy models, and it's a very rich field, and there's a lot in the future, I believe. Yeah. Thank you.
Questions? Okay, we have a question there.
Yeah.
And,
I have a question.
allá, hasta allá.
Yeah.
Aquí.
Hi.
No vamos a poder todos, ¿de acuerdo? Porque él se va a cansar. Entonces, por favor, calma.
First of all, I want to start off by thanking you, Professor Haldane, for your wonderful presentation. So you mentioned that the topologically protected qubit could be the solution to the scalability and the decoherence problems, ideally. So my question is, what would it take to get there practically?
Okay, well, the Majorana modes are they're not the full, they're not the universal quantum computing device, but I'm still waiting to see what exactly Microsoft have managed to do with them. They've announced, they made a lot of very nice YouTube movies about it, and I'm going to hear a talk by Chetan Nayak later in November. We'll find out what's actually going on. The difficulty has always been the fact that the real-life systems have some exponential decay length. The topology mathematically sounds clean and perfect, but there's a length scale involved. The things have to be further apart. In the quantum hole, the edges have to be further apart than this length scale for which the edge states decay into the bulk. And once that's achieved, you've got topology. But the problem had been with the Majorana zero modes, as far as I know, that the question is how much localized they can be at the ends of the little kind of H-shaped object inside the Microsoft thing with the 4 qubits, 4 Majoranas, one on each end of the H. But,
Okay.
and there's the issue of quasi-particle poisoning, and I mean, on paper it looks great, but you can't tell till you actually see a working version, just like fusion.
Okay,
I have a question, another question.
there was another question here. Which is
here.
last and that one. Okay, you and you are going to be the last.
My question is, what is your philosophical stand about quantum mechanics, and if you have a favorite interpretation or a personal interpretation about quantum mechanics?
I don't worry about it. As a human being, I believe I have free will to make decisions, and that everything I decide to do wasn't decided by the initial conditions of the universe, whatever those may be. Thinking about something like the wave function of the universe and who collapses it sounds like a kind of not a very profitable idea to think about. I think one has to be guided only by things that can be resolved experimentally. Otherwise you're talking, and so that's what John Bell's big achievement was, to turn Einstein's criticisms of quantum mechanics into a very concrete set of things you could measure experimentally and rule out local realism ideas if you got certain results, in which when you do the measurements you actually do exactly rule out local realism. So whether it's, I don't know how useful it is to worry about the ultimate meaning of quantum mechanics until you can formulate it in a kind of experimental question. So it doesn't worry me. I see a contradiction between supposedly quantum mechanics, the whole issue of free will in quantum mechanics. Those are kind of philosophical questions, and what's happened in recent years is things like entanglement has been turned from a philosophical question to a technological question.
Aquí. A ver, aquí a ella. Sí. ¿Puedes darle el micrófono?
Thank you,
allá,
Professor.
Allá, por favor. Allá, ¿cómo te llamas de amarillo, la muchacha de amarillo? Sí. Y va a ser la última pregunta que tomamos porque él está cansado, ¿de acuerdo? Le cansa un poco la altura de la ciudad de Toluca.
First of all, I want to thank you, Professor, for sharing your knowledge in such a beautiful way. And my question is, how can we take two particles that have been entangled before and disentangle them? You mentioned that even if we separate them so far away, they're gonna still be entangled. So how can we undo that entanglement?
Well, they've done that. The entanglement that's been shown over large distances is with photons, and they've done these teleportation experiments now, and done Bell experiments on them. So photons can remain entangled over large distances, and so there's a huge amount of work on trying to use this for things now. Yeah.
So it's about the distance. It's about the
a photon can travel a large distance without interacting with the environment. Like we see photons that come from shortly after the Big Bang, right? Before that, the universe is opaque because the charged particles are all liberated. But after they collapse to form atoms, the photons liberated at that time became the microwave background, right? So yeah, photons are a very robust tool for things, and you know, there's attempts to make quantum computers out of superconducting qubits, out of Rydberg atoms is also very promising, which are addressable. Photons are also good, but they're not so addressable as things like arrays of Rydberg atoms or trapped ions, where you can actually, you know, measure them individually. But photons work great. Yeah.
Okay. Thank you so much.
Okay, we thank again Professor Haldane, and we are going to give him a gift from the Sociedad Mexicana de Física. Muchas gracias, profesor.
Okay. Ah, thank you.
No me llevo el micrófono, ¿te quiero decir? Es un árbol de... It's the Tree of Life. This was made in Metepec, Estado de México.
Muchas gracias.
Queremos darle las gracias al profesor Haldane por esta charla tan interesante. Vamos a tomar una foto. Él va a colocarse desde acá y entonces tomamos la foto así y después podrá ver algunas firmas. Él se sentará acá y las firmas serán pasando para aquel lado, pero se va a colocar solamente aquí y la foto hacia el fondo.
Yeah.
You just stay here and for photographs, just take a picture. And so some, no problem to take a picture here, but maybe you can just sit down and there's a line just from. But first of all, the photo. Yeah, just here, but bigger. In the other side, just looking. Ok, gracias. Entonces ahora sí va a haber una... Ok, thank you so much. Perdón, muchas gracias. Ahora entonces habrá algunas firmas de autógrafos o saludar al profesor Haldane, pero hay una línea del otro lado y van pasando para acá, por favor. Solamente será unos minutos. So please just sit down here and whatever you want. Here,